we have now Amlan Banaji talking to us about Fourier for conjugate-to-linear.
Okay, thanks, Duncan. Yeah, and thank you for the invitation to come here as well. I think it's a really nice format. I think it's smaller things where we can discuss things in more detail. It's been really nice so far. Some of you will definitely have heard various parts of this before, so apologies for that. But hopefully, I'll present it in a slightly different way and kind of emphasize the analytic aspect of things that I talk about, and which should fit into the theme of the workshop quite nicely, and maybe I'll try and get to some of the high dimensional stuff a little bit as well, which is maybe not so much that I've talked about before. Okay, so I'm going to talk about Fourier decay for self-conformal measures. So first of all, let's just make a standing assumption to rule out various trivialities. So in this talk, all self-similar and self-conformal measures are going to be non-atomic. So they're not going to just be a single atom, otherwise everything that I'm going to say will not be true. And the starting point here is a theorem, which I'm going to call the analytic theorem, which I'm sure many of you have now seen before, which says that let nu be a self-conformal measure for an IFS or maps by I from the unit interval that they into itself, and each of these maps is going to be real-analytic. Then, and we're also going to assume a non-linearity assumption. So there exists some I such that phi I is not an affine map. Then nu as polynomial Fourier decay. So what do I mean by this? I mean that the magnitude of the Fourier transform of nu, the frequency psi, is going to be bounded up to some uniform multiplicative constant by psi to the minus eta of some eta greater than 0. And maybe I'll use the node polynomial for any level. Yeah. Okay. And the notation, the way that I'm defining the Fourier transform in this talk is just going to be the integral e to the minus 2 pi I psi x du of x. So this comes from combining various maps. There was an important paper by Algom-Chang-Wu-Wu and one, and then they proved something that was a bit similar to something that Baker and Salston proved. And then I also proved some work with Simon, and then there was another paper by Algom-Chang-Wu-Wu, and kind of putting everything together, you get this result here. And in this talk, I'm going to assume throughout that the IFS, let's call it capital phi, is real-analytically conjugate to a self-similar IFS. So what does this mean? This means that there exists some real-analytic diffeomorphism F such that let's see the notation that I use here. Yeah, so F composed psi composed F inverse psi I composed F inverse equals phi I for all such F will simultaneously conjugate IFS to some similar IFS. Okay, and so yeah, this talk I'll assume this throughout, but the non-conjugate case will be discussed by Simon in this talk very soon. So I won't say anything more about the non-conjugate case for now. Okay, now if we make this assumption, then the first thing to notice is that nu will in fact be a push forward of a self-similar measure by the conjugacy map. So let's suppose that nu is defined using the weights pi. Pi are always going to be strictly positive probability weights. And that mu, sorry, be the self-similar measure defined using the same weights. Then we can simply observe that if we take any or L step A in the real line, then if we look at the push forward measure, so this is the push forward measure defined by mu of F inverse A. Then this is going to be the same thing as the sum of pi times mu psi I inverse of F inverse of A by self-similarity, which is equal to the sum of pi times mu of F inverse composed by inverse of A, right? This is using this conjugacy relation over here, rearranging that. And this is simply the same as the sum of pi times phi I of this push forward measure by F of the set A. So therefore, this push forward measure F mu satisfies the self-conformality relation that the self-conformal measure satisfies. So the conclusion is that nu is equal to F. So these conjugates within these self-conformal measures can be realized as push forwards of self-similar measures by the conjugacy map. So for now, we can basically work with push forwards of self-similar measures in this talk. And since some map by I in our IFS was non-affine, also F is non-affine. Right? So we're pushing forward a self-similar measure by a non-affine map. So in this conjugate to linear case, our analytic theorem reduces to the following theorem. which I call the pushforward theorem.
Sorry,
Yes.
could you use a different marker? Yes, thank you.
This is proved by Simon Baker and myself, and then independently and simultaneously by Algom-Chang-Wu-Wu, Chang-Wu-Wu, and Wu. And these are both published in 2025. And the result is just what I said before, so that mu be a self-similar measure on the real line, non-atomic as I always assume, and a map on some interval of the real line which contains the support of mu into the real line, non-affine and real-analytic. Then the pushforward measure has polynomial Fourier decay. And what this means is, we know what this means. Of course, it's saying that this is the case for some small exponent eta, but now this by the chain rule is just the same as the integral of e to the minus 2 pi I sine f of x du of x. So we kind of changed x to this nonlinear phase f of x. Okay. So I want to give you some idea about why this theorem is true in this talk. And yeah, so the two proofs are quite different, and the proof with Simon uses this disintegration technique, and I'm not going to talk about that proof at all actually in this talk. The one that I talk about will be a bit more closely related to the one by Amir and co-authors. But I'll present it slightly differently in a way which makes it as easy as possible to see about higher dimensional generalizations as well. Okay. So in order to prove this, we need to use two key tools. So the first tool is going to be decay. I'll say I'll be more precise. Fourier decay. Outside sparse frequencies. This is for the self-similar measure mu. Actually, first of all, I should just mention in the analytic theorem that I said right at the start, why are the assumptions needed? Well, of course, we need the nonlinearity assumption because we have examples like the Middleton-Cantor measure, which are not even Eichmann, but the Fourier transform doesn't decay at all. So we have to have some nonlinearity assumption. And where does analytic come in? I want to explain that in the next tool that I'll talk about. But even for non-Eichmann self-similar measures like the Middleton-Cantor measure, they do have Fourier decay outside of very sparse set of exceptional frequencies. And the measures in the line, this was proved by Suchi from I think 2015. And the statement is that mu is self-similar in the line. Then if we And then we let epsilon be any positive number that exists. Positive numbers delta, which is very small, and c, which is very large, maybe, such that if we consider the set of frequencies psi between minus r and r, where r is some large real number here, for which the Fourier transform of mu does not decay very fast, so this in magnitude is larger than the modulus of psi to the power of minus delta. Then this can be covered by at most c times, sorry, I think this should be in r here actually. Yeah. C times r to the epsilon intervals for length 1. And let's call these intervals some future equals J1 up to J times the thought function of C times R to epsilon. So this epsilon is as small as we like, but then as we make epsilon smaller, we might have to make the delta smaller here in order to compensate. But I want to emphasize that this is a really sparse set of frequencies. So you should not think of this as like a zero measure set of frequencies in the minus R to R. You should think of it like a zero dimensional set of frequencies. Okay. And yeah, in the one dimensional case, this was proved by Suchi, but I haven't actually really looked at the proof of this because now the best way to see this is to use work of Osama Khalil, because that will then generalize to higher dimensions much more nicely. Okay, and then the second tool might seem a little bit strange to state it in this way, but in the higher dimensional case, we will need to state this as a separate tool. And actually, one of the main difficulties in extending to the higher dimensional case will be the extension of this tool. I'll call this a Fourier type inequality that has similar measures, and this says in this setting that if f is an analytic map on some interval in the real line, then there exists some positive exponent theta such that for all deltas small enough, lots of delta small enough, if we consider the self-similar measure, so mu here in the self-similar measure again on the real line, or the set of x for which f of x minus some number y is very small, smaller than delta, then this can be bounded uniformly by delta to the beta, some exponent beta, which is positive. And what is y? So this has got to hold uniformly. For y in a compact set. So why is this true? This is true because I'll just give you a brief idea. We can consider finite set pre-images applied by our analytic map F, right? So this is using analyticity here.
Amlan,
Yes.
can you hear me?
Yeah, I can hear you.
Oh.
Right.
How are you? Are you?
I'm good. Yeah.
Nice to see you. Can you say a word about tool 2? For example, does the beta depend on the measure, or is it uniform across all self-similar measures? And like, is there some kind of non-concentration Boolean type thing?
So it depends on the measure, but the beta will be uniform across y, and it will be uniform across, in this case, we just have one analytic function, but it will also be uniform across a compact family of analytic functions in the compact open topology. But this is like a very basic one-dimensional version of this, and I want to, later on, if I have time, I want to state a higher dimensional version which should shine a bit more light on this theorem. Yeah.
Thank
Does
you.
that answer for now? Yeah.
Yeah.
Okay, cool. Yeah, in the one-dimensional case, this is quite easy because we only have a finite set of pre-images at point y, and we can Taylor expand about each point, and we can see polynomial growth function f as we move away from the point y. So if we look at f of x minus y, this is going to be uniformly bounded below by the difference of, so let's say, if we call that point 10, if that's Taylor expanding around, then this is going to be uniformly bounded by the distance of x minus z, the sum m, where m and b is the constants are both uniform, and therefore this set is going to be contained inside finitely many intervals, each of whose length is going to be some power of delta. And so now we just use that there exists some positive Frostman exponent, let's call it kappa f, which is strictly greater than 0, such that the self-similar measure of an interval minus r, let's say, is uniformly bounded by r to the power of kappa f. So say self-similar measure something positive for Frostman exponent. And this was due to and Lau from maybe 2000 days. Yeah. So this really crucially uses the analyticity of a function. Can it fairly clear why the analytic implies this Wish image type inequality? Okay, so then this is really the key part of the proof where we use the assumption that our push-forward function is analytic. And I just want to say, well, what about if we don't assume that our function is analytic? Obviously, the proof of this doesn't work, but what about the results themselves? Are they still true? And it turns out that they are not. Okay. So this is separate joint work with Simon, which I don't want to go into too much, but I'll just say that if we replace analytic by C infinity, then both of these theorems, the analytic theorem and the push-forward theorem, fail back as well, because there can exist examples which are Deichmann, but which have decay as slow as we like, along some sequence of instances. So not only does the proof break down, the results themselves are completely false in the C infinity category. Okay, so how does the proof of the push-forward theorem work? Well, let's let psi be some large frequency, and let n be an integer such that psi is going to be roughly 2 to the power of 1.5, and we want something between 1 and 2 here instead of 1.5. The precise value 1.5 doesn't matter too much unless you're trying to optimize the exponents. But in this case, we are really not trying to optimize the exponent at all, because we use the relationship between epsilon and delta here that's given by Tsuji, and this is not well at all. And also the bidirectional versions is very far from optimal. So yeah, one more comment related to this is that this proof method, I'm going to say, doesn't really give you very much information about the optimal exponent. We're just trying to get some positive exponents to prove. Okay. You have to do things a little bit differently and impose some more assumptions to get quantitative bounds. And I've done that in some cases, etc. But that's not what I'm going to talk about today. So let's let I sub n be a 2 to the minus n stopping of the IFS. So what do I mean by this? I just mean that it's a collection of finite words such that this is the IFS maps psi. So mu is going to be equal to the sum of over W in this set of PW psi W of mu. Let's call this little piece of the measure psi mu W, sorry, is mu subscript W, right, where the diameter support of mu W is roughly equal to 2 to the minus n up to some uniform constants. Right, so taking all of the different little pieces of ourselves similar measurement, potentially overlapping, and each of these lengths is going to be roughly 2 to the minus n. I can say that here we allow arbitrary overlaps in all of these cells. So that's one nice thing about these derivatives, that we don't assume any kind of separation assumptions on our source of the measure. Okay. So then, if we consider the Fourier transform of the image measure at the frequency psi, then we can write this as, well, the integral e to the minus 2 pi psi f of x d mu of x. And this we can bound by the triangle inequality. We can take the sum over all of these words w in our 2 to the minus n stopping. Yeah, pw times the magnitude of the integral e to the minus 2 pi I psi f of x d mu w. Okay. One more comment about the optimality. So here we use the triangle inequality and we just take the modulus of the Fourier transform of each of these little pieces. And this ignores the fact that some of the different points on the unit circle and complex plane which we're averaging might have some cancellation, which might help us, right? So so basically what I'm trying to say is that there could also be a lot of loss in this stage right at the start. So already we're kind of ruling out the possibility of hoping to get any kind of sharp exponents using this strategy.
F should compose the phi n.
It's a mu omega.
Mu omega.
I guess F compose the phi n or something. The psi omega compose psi omega.
Is it? I thought that because so mu omega is already psi omega. Yeah. But yeah, exactly. You could put a mu here and then bring out. That's okay. That's good. Okay. So now, right. So now we can break this down into different parts corresponding to the contraction ratios of the maps in the R-stopping. So we can sum over all of those possible contraction ratios in IN, and we can consider only those elements of the sum for which the diameter of the support of mu omega is equal to r. This would be helpful. But now, there's only polynomially many possible contraction ratios, because essentially of the commutativity of multiplication of real numbers. So we don't really have to worry about this. We can kind of assume that our self-conformal measure is homogeneous and we don't lose very much by making that assumption. Or rather, the proof strategy in the homogeneous case will be essentially the same as in the general case because of this simple fact that there are only polynomially many possible R, which is something over here in N. Okay, so polynomially many R, N, and the rest of this term will give us some sort of exponential term in N. So for the rest of this time, we're going to assume that mu is a homogeneous subset measure. And all of our contraction ratios are going to be equal to the diameter. So the diameter of the support is being omega is always going to be equal to some Rn for all omega in IN, and this is going to be roughly equal to 2 squares. So we can get about this. Then for each omega, we're going to fix x omega in the support of mu omega, and we're going to Taylor expand f around this point. So fx is equal to f of x omega plus n prime of x omega times x minus x omega plus something of the order x minus x omega squared. And now if we think about what this does inside the integral here, well, x omega is a constant inside each of those integrals. So f of x omega is just going to change phase. It's going to rotate you around the unit circle, so it's not going to affect the modulus of this integral at all. So we can ignore this. So let's see what the other two terms give. So if we now carry on from this over here, then Fourier transform of this is going to be bounded up to some multiplicative constant by the sum of omega p omega times the Fourier transform of mu omega at the frequency given by the derivative of our push forward function f times like psi. And then we need to add on the error term that you get from this error term in the Taylor expansion. And this is just going to be the magnitude of psi over 2 to the 2n. And now this is useful, the fact that we've chosen psi to be this large, so psi divided by 2 to the 2n is going to be something which decays polynomially in psi. So here we're going to get a polynomial decay in psi. Just forget about this term. So what about this term? Well, this is going to be equal to the sum of omega and in p omega times. And now what I want to do here is to use self-similarity. Because so far we haven't really used it in an important way, but now we can translate each of these little pieces of our self-similar measure that doesn't affect anything, and then rescale to see that this is the same thing as the magnitude of the Fourier transform of the self-similar measure mu itself, right, which is omega scaled up by the factor Rn. But now we've got to change the frequency. So we're going to get a factor of Rn inside the frequency. Let's rescale. And now what we can do is we can now apply decay outside sparse frequencies, so from 2G, to break this sum into those words for which this frequency lies inside one of 2G's bad intervals, into those words for which this frequency does not lie inside the bad 2G interval. This is bounded by the sum of I equals 1 up to the law of C times 2 to the epsilon n, sum epsilon. And we're going to sum over those words for which this frequency Rn f prime of x omega psi lies inside the interval Ji. And then we have the weight, the omega, and then we're just going to use the number 1 here because we don't know anything about the Fourier transform of mu inside these bad intervals. But then for the remainder of the sum, we know that the Fourier transform of mu is always going to be bounded by the number r to the power of minus delta. So we can get a bound psi divided by 2 to the n. And if we rearrange this, it's the power of minus delta for the words which end up. So this is like for the sum of all of those words which end up in the good frequencies according to Suji. And once again, because of the way that we've defined psi with this power somewhere between 1 and 2, this gives you some power decay in psi, and we're happy with this term over here.
There is power
Yeah, so this is using the definition of decay outside sparse frequencies. So we're covering these intervals I J sub I are those intervals for which the magnitude of the Fourier transform of mu is larger than just the minus delta. So this is all of the rest of them. Okay. So Now, to bound this term over here, we are going to use the Weierstrass type inequality. And this number being inside an interval of length 1 is equivalent to the piece of the self-similar measure being inside an interval of length Rn divided by psi. So then we can bound this term by Rn divided by psi to the power of beta, which was the exponent from the Weierstrass type inequality. And this is roughly going to be 2 to the n of xi to the power of theta. And once again, by the way that we've chosen our size of our frequency psi, we get power for decay for this term as well. So I hope that's gives a reasonable idea about why this Pushforward theorem is true, assuming those, well, assuming the main bit that I didn't show is this decay outside sparse frequencies after stage. Right. So now I want to say something about higher dimensions for the rest of the talk, if this is all okay. And I'm going to work mostly in the plane because, well, I can say something, you can ask me some things about even higher dimensions if you want to, but in the plane, as Joe was saying, you know, self-conformal measures are more interesting, there's more of them, right? We can take all polymorphic maps in our IFS rather than just Möbius transformations. So what the 2D version of the analytic theorem? Well, let's let nu be a self-conformal measure inside complex plane for an IFS of polymorphic injective matters. And now, in Joe's talk from yesterday, he was taking a lot of care to make the most general possible setup. I'm going to do the exact opposite and just assume that we are going from the unit ball into itself. Although this can surely be relaxed somewhat. Certainly with conjugate-to-linear case, it can definitely be relaxed. Okay. And let's assume there exists some I such that phi I is not affine. Otherwise, we could take, for instance, the products of the counter-Lebeau measure with itself, and this will not have decay along powers 3 along the x-axis. And now we need one more assumption. We're going to assume nu is not supported in an analytic curve. Right, so the not supported in some analytic image of complex analytic image of a unit interval. Then I think this is all we need to conclude that nu has polynomial pretty good. Unless that missed some assumption. Okay, and the proof of this again breaks into two cases. So first of all, the non-conjugate case was proved by Amlan with Federico Rodriguez and Erdős Center. 2025. This group of authors, they have lots of papers together, so this is one of those papers, not necessarily the most famous one maybe. And the conjugate case is what I want to talk about now. So this is a recent rewritten with Anu. So what do I mean by the conjugate case here? I mean that there exists some holomorphic diffeomorphism F such that, once again, each of our phi i's is equal to F composed psi I composed F inverse, so the psi i's are similarities. Okay. And we say a word or two about the assumptions here. So, well, holomorphic is essentially because these are just about the only formal maps in two dimensions.
My book Gillibo said that you can put the rest of them at movie.
Thank you.
Okay,
Great. Thank you. Thank you very much.
Spanyol, hogy félbe tudnak fogadni ekkor nem.
De igen, az tökéletes, az egyben azt kérték, hogy 12 óra 10 körül. Na, az akkor dél, az jó.
Jó.
Jó, köszönjük.
Right. So it's the which is much more interesting.
Yeah.
But yeah, so this is just because holomorphic maps are informal, and but also we need kind of the real-analytic structure. Well, actually, we will use this quite crucially in many ways. Yeah. The reason why we assume it's non-affine is because of this kind of productive transformation measure kind of examples. But now I want to explain why we need this assumption that we're not supposed to in an analytic curve. And the reason for that is because we have these interesting examples where we can let mu be cancel the Bay measure on an interval 0 and 1, for example, and let's let f of x be equal to f of z actually be equal to z plus I z plus 1 squared. This is some holomorphic map, and it takes a point on the real line, so it takes x to x plus 1 squared. Right, so it's kind of lifting the cancel the Bay measure onto a parabola like this. Then mu, which is equal to f mu, is self-conformal for the IFS, the conjugate IFS. F inverse probably composed x over 3 times f, and then we said the map is going to be f inverse composed x plus 1 over 3 times f. But the point of the vertical projection of this measure down to the x-axis is just going to be a cancel the Bay measure, which is non-diaphragm. So we should look at the Fourier transform at frequencies of the form 3 to the n 0, and this does not decay to 0 as n tends to infinity. So this is why we need this assumption that we're not supposed to curve. And let me also say this is a self-conformal measure. Just a fun fact is I think this is also a self-affine measure, because there's this parabolic transformation which sends parabola onto itself, which is an affine map. So this is both self-conformal and self-affine, but the point is that the conformal and affine maps, they do the same thing on the parabola, so on the attractor they do the same thing, but outside the attractor they do completely different things. So I really like this class of measures, let's study them some more. Yeah, keep them in mind.
the self-conformal sound like but not so similar is the point.
Yeah, exactly. Even though it can fall. Yeah. Okay. So, saving the remaining time. So, in the conjugate case, as one would expect, this reduces to the push forward theorem. So it reduces to the fact that if we have a self-similar measure on the plane, self-similar on the complex plane and not supported in a line, or else the push would be supported in a curve. Right? And F is going to be defined on some neighborhood of mu, and it's going to be polymorphic, non-abiding. Then the image F mu as a polynomial Fourier. Okay. And how do we prove this? Well, first reduction to notice is that since F is polymorphic, it satisfies a non-degeneracy assumption, which is what we will need to prove a more general type of push-forward statement from Rk to Rd. So in particular, polymorphic means that we can use the Cauchy-Riemann equations tell us that the graph of F Z F of Z in this domain. So this is a subset of C2 or R4. And this is not contained in an affine hyperplane inside R. And this graph of the function not be contained in an affine hyperplane is exactly the non-degeneracy condition that we need. Although in higher dimensions, we think this is the right condition, but there's some examples of functions that satisfy this where we're not quite able to prove that. Yes, this is in dimensions 3 and higher. So there are some additional complications in dimensions 3 and higher for the push forward result. And now the variants of the two tools that we need are, first of all, the decay outside sparse frequencies. So if mu is self-similar on the complex plane, or more generally on Rk, then mu has decay outside sparse frequencies if and only if mu is not supported in an affine hyperplane. Okay. So if you are supported in an affine hyperplane, then you have no Fourier decay or orthogonal directions, so clearly you can't have decay outside sparse frequencies. The difficulty is all in the reverse direction. And okay, this is technically it's first written down in my paper with Han, but it very heavily uses work of Osama Khalil from this year, which in turn is based on the inverse theorem of Mike Hochman, which was a joke presented in his talk yesterday. And the second tool, I think that might be the last thing I have time to say, is I just want to state the more flexible version of the Weiershevich type inequality for self-similar measures, and maybe explain why it's called the Weiershevich type inequality, because I hope that this inequality might have a broader use beyond this particular problem. For one prime, 2 primes. This is Weiershevich. And this says that, and yeah, this is from my paper then. If you actually, let's say if A is a compact family of real-analytic functions from some domain U of Rk into Rg, and compact here is inside the compact open topology. You know what that is. We assume that 0 is not in this family A, otherwise things go wrong straight away. And we're going to let mu be self-similar in Rk, not contained in a hyperplane of Rk. Then don't worry too much about the epsilon. This is not really the key point, but this is the version that we're going to use. But in this theorem, but for all epsilon greater than 0, there exists some, let's call it beta, greater than 0. So beta here, it depends, just to kind of address Samir's point from earlier on. So it depends on family A and on the self-similar measure mu, but not on the particular function f in A, which is important, such that if we consider the supremum over all functions f in this analytic family of the measure mu of the set where f is less than delta, and then actually we want to expand this a bit, so we want to take a delta to the epsilon neighborhood of that set, but again, don't worry too much about this. And this should be bounded by delta to the beta. And once again, this constant here can depend, I think, only on mu of A, that it's got to be uniform over functions f in this family of analytic functions. Okay. And once again, this really crucially uses the real analytic structure of the functions f, and the reason why it's called a Weiershevich type inequality is because the classical Weiershevich type inequality tells you that if you have a real analytic function, then it might have some 0 set, right, which would be some analytic variety, and then the inequality tells you that if you move away from your 0 set by some delta, then your function at this point over here should be greater than or equal to some power of delta. Yes, so you move away from the 0 set, and you increase by a power of the distance of which you move away. So this can kind of be translated into a form which says that the Lebesgue measure of the region where you are, where your function is at most delta, should not be too large. It should be bounded above by a power of delta. But now, instead of the Lebesgue measure for this problem, we need it for a self-similar measure. Yes.
Can you replace
self-similar that postman?
Well, I don't know. Our proof uses self-similarity quite a lot because we look at all the different pieces of our self-similar measure around it, and then look at the small pieces inside that and show that you get this balance. So I can't see straight away how you do it. But yeah, that's what I was just saying. Thanks.
Right, do we have questions?
Yes, you know, like, so say that you're in arcade, but instead of having a self-similar measure, you have some, I don't know, invariant measure or some many system. So I can really diffeomorphism or something like that. Would you expect the same thing to if you have some sort of a similarity?
So you want to take a measure which is defined in some sort of dynamical way and then push it. But that's I'm not really a map.
Not specifically this.
Oh, this thing. Yeah, I think it's plausible, but if you have enough self-similarity, then this might hold. You want to say that if you take the region where you're bounded by delta, then if you make this region uniformly small enough, then there should be some piece of your measure which lies outside the region, and then if you make this uniformly smaller again, then you've got to each of the pieces which lie inside this region to be some piece which lies outside here. So if you can make this kind of argument work with a more general class of measure, then I think there's a chance that you can get this together.
Yes.
So you state this push forward theorem in 2 dimensions. But if you were to push forward in higher dimensions, you don't have the commutativity of your orthogonal paths and the
Exactly.
yeah, but am I correct in saying so how crucial is this?
Yeah, so
Pretty much if you want to higher dimension.
yeah, so we would conjecture that if you take some affine irreducible self-similar measure in higher dimensions and you push it forward by a map which is non-degenerate in this sense and real-analytic, then you should have free decay the push forward. We can prove that if the rotation group is small, as you say. If the rotation group is large, then we can impose a stronger non-degeneracy assumption than this, which rules out cases like x goes to the modulus of x, whose graph is a cone, because the issue here is that you're then going to get a set of frequencies which all lie on some sphere in 3-dimensional space, and you have no control over the rotation matrices, and maybe these rotation matrices will rotate all of your bad frequencies into a single, all of your frequencies into a single frequency, which is a bad Suji frequency. I mean, it feels very unlikely that should happen, but if you're right, that might happen. So we need to rule out examples like this in order to get the theorem of high dimensional push forwards with this expanding rotation group. But yeah, in principle, obviously having an expanding rotation group should help you, but the proof doesn't quite work. So there's still something more to be done.
So in this example you gave of this affine self-conformal measure,
Yeah.
so somehow we can see that it's push forward in one direction, you don't have properly nonlinear because now, I mean, let's suppose, so I think this is a push forward from R2 to R2, the second derivative, the first component is 0. I mean, what if I just assume that all of these 2 components, if I give it as a function from R2 to R2, or their mixed derivatives with respect to x and y and never 0, is that then do you get what you were hoping for?
Yes, as long as you don't have some direction such that your push forward, you then take a push forward and you then project onto that direction, you get an affine map. That's going to be construction. Yeah, then if you don't have that, then you get the decay.
Okay, so
Yeah.
Sorry, we are running a little bit late for us, so we're just waiting for us right now. We can ask Amlan anyone later, 90 days, so let's say Amlan again.
Okay.